So hello, this lecture is going to be about looking inside the GPT and various aspects of everything from the architecture to all the nuances of what hyperparameters we should be using, how wide and long the neural network should be, what kind of positional embeddings I usually use in production for all this explosion of open source LLMs, and even we have some good indications of what the closed source LLMs might be using as well. So this lecture is basically going to be about how you can implement stuff from scratch and understand things, because I think that's the best way to teach yourself something, to basically implement something and understand what the nuances of the production system might be, as opposed to just reading about it in a research paper or just viewing some slides. So the major contents of this lecture is going to be tokenizing, the architectural consensus of the research community on various aspects, with its pre versus post norm, RMS norm, why not layer norm, or many other normalization techniques, what activation functions might be used, so many of them, which ones are most likely to be used, positional embeddings and the transformer block, and the hyperparameter selection, which involves a lot of things, whether it's the dimensionality of the various layers, how many heads we are using, how long and wide the neural network should be, and finally some ML systems understanding of grouped query attention and multi-query attention, because a lot of recent work has involved a lot about trying to make the model more efficient, reduce the cost of the attention heads, and obviously stability tricks. When you're training these huge humongous models on so many GPUs, you just want to make sure you're doing it in the best way possible, and there are quite a lot of tricks throughout the architecture and the training procedure you can use to make sure you're doing it in the best way possible. So tokenizing is, I would say, is one of the boring parts, but is extremely essential nonetheless. I would highly recommend you look at Adar Karpathy's videos on a lot of these topics and tokenization as well. I think he does a really good job of implementing stuff from scratch, just the way I would like someone to teach me that way. So I would highly recommend checking it out as well. So as for tokenization, let's start. So basically, it's tokenization is about converting raw text into a sequence of integers. So raw text is usually represented as Unicode strings on the internet. UTF-8 encoding, I think, is 98% of the internet. So basically converting them into a series of integers which are actually ingestible by an LLM. So we need a procedure to convert these, encode these strings as well as decode them. So it should be a reversible process. And another important thing in tokenization is the vocabulary size, like the number of possible tokens. If there are way too many tokens, it would be inefficient. And if there are way too few tokens, then it might overfit to some of the tokens, and it's not ideal. So this is a good example of this website gives you good indications of what is happening under the hood in a tokenizer. So as you can see here, this sentence is basically tokenized into various tokens, which is visible right here. So you can probably see a few interesting observations might be hello is different tokens at different places, and here it's space hello, and here it's just hello. So there are different tokens. So even spaces before the words, that's usually how it works, like spaces before the words and the words are different tokens. And also an interesting observation might be how it's encoding numbers, I guess. So we humans usually do right to left, but this seems to be doing left to right, which is an interesting observation. Repeat characters might have some other nuances, the way it's getting tokenized. So let's now talk about these are the observations we made. Just talk about some aspects of tokenization. It should obviously be reversible. The string we tokenize and the reconstructed strings should be the same. The compression ratio is an important one, which is the number of bytes which our initial string contained and the number of tokens we end up using to represent the string. So compression ratio is basically how much information we are compressing in the inputs. So kind of projecting our input into a smaller scale and trying to see how much information we can actually encode. So, what kind of tokenization techniques which comes to mind when someone says you're going to tokenize a sentence? So, I'm going to talk about trade-offs or the various intuitive techniques you might come up with. So, character-based tokenization is one of them. This is very reasonable that you're basically uh, each character would be an individual token. For instance, A is 97. This Earth emoji is 127,757. Quite a large integer, but yeah, that's its Unicode tokenization. The problems with it is there's 150,000 Unicode characters, so the vocabulary size is extremely high. And extremely high vocabulary size is inefficient, especially with tokens like Earth emoji, which is very, very rare. So it's not something which is used quite often. So using that and including that in the vocabulary is not the most efficient, while the tokens which do happen to come quite often might not be included in the vocabulary because they are not Unicode characters. And the compression ratio is 1.53, which is not too bad, but yeah, not something very good either. So next is byte-based encoding. So basically converting our text into a series of bytes and having each of the byte as a separate token. So this is definitely also a reasonable and quite elegant way of tokenizing. But the only problem, of course, is that sequences would be extremely long because they would be divided into individual bytes. So you might say the quality of the model would improve quite a lot because the self-attention which we are doing with the transformer block might involve a lot of tokens even within a word to give attention to each other, which might give some insights. But still, the compression ratio is very, very bad. It's just one. Sequence is very long, so the inference and optimization and the inference would be highly ineffective. So word-based tokenization is something which I would say is closer to what is classically done in the NLP, is to split strings into words. So string like this shown on the screen, I guess would be converted into the individual words within them. So GPT tokenization expression is given as well. Compression ratio is also not too bad, but the problem with it is that number of words is huge. Like it's basically unbounded. So there are many words which the model might see during training, but they would not see it during inference. Many people misspell many words, so there would basically be a new special UNC token, which is ugly and can mess up perplexity calculations. So many words are rare and the model won't learn much from them either. And this obviously doesn't provide a fixed vocabulary size, as I said, and the compression ratio is also not exactly what we want. So then comes the one which is used by the industry most commonly, is byte pair encoding. It was first introduced by Philip Gage in 1994 for data compression. It was adapted for NLP in neural machine translation in 2015 and used by GPT-2 as a tokenizer. So the basic idea is to train a tokenizer on raw text to basically determine the vocabulary itself. So huge corpus of text, and the goal of the training would be to help the tokenizer understand what the vocabulary should be. So hopefully the corpus we are training on will be representative of the test and the validation set. And the intuition is that common sequences of characters would be represented by a single token, while the rare sequences represented by many tokens. So this basically compresses the information in a very nice way. And yeah, there are many similar compression techniques throughout computer science, which basically is analogous to what this is doing, byte pair encoding. So the GPT-2 paper used word-based tokenization to break up the text into the initial segments and run the original BPE algo on each one. So converting into the initial segments, I think, is an effective way of doing it. So basically doing some pre-tokenization before you do the character level merging. I would go more into the details of this algorithm in just a second. So start with each byte as a token and successively merge the most common pair of adjacent tokens. So find the most common pair of tokens and basically merge them and make them one token. So I have this file right here to give you an idea of how this works. So this is an example. For instance, we are training a tokenizer on just this sentence. This is very unrepresentative of what usually happens. There's probably a huge corpus of data which we train the tokenizer on. But for the sake of this example, let's say we are training a tokenizer on this and trying to see what we can merge within this. So if we basically start with the string, we have the initial UTF-8 byte indices for this. So there are 14 indices on this. And then we start our first merge operation. So we go through these indices. We first add this. So we are counting the number of pairs of various indices which occur together. So we do it quite some time and see which of these pairs are occurring more frequently together. For instance, 97 and 110 and 97 110 has occurred twice. So it's right here, it has occurred twice. So at the end of the round, we'll basically see which one has occurred the most frequently together and basically create a merge of these, like A and N would be merged together as a new token ID and the vocabulary would be updated. So initially the vocabulary was just 255 characters. Now we have added the 256th character, which is AN. And we can replace, we update the vocabulary, update the merges, and the new indices after the merge would be slightly smaller than what we had initially. I think it's like 1 token less, I guess. We can do this as many times as we want to see what vocabulary we would want, like how many merges we want. It depends on how much we want to compress this information, I guess. Okay, so I had set it to 3 merges. So we have done the 3 merges and we have the vocabulary at 258 now. And if you look at this now, the final learned merges are AN, BAN, and ANA. So it kind of makes sense that these were the merges we did here based on this, because these seem to be occurring quite often together. So tokenizing them together would make sense. So initial length would be 14 and the compression ratio is 2.33. The final indices were 6. So yeah, compression is pretty good on this one, but obviously this is just an example. The GPT-2 tokenizer has an approx compression ratio of 1.27. Now, just to give you an idea of how it is working in production as well. So this, you can probably look at it in the GitHub I have in the description. So this is a training loop which actually is much closer to what it looks in production. So the train BPE takes an input path to the data file and the vocabulary size which we want and the special tokens. So usually the data which we train on has a lot of special tokens like end of text tokens, where it basically demarcates the various different files which go into making the training corpus. And we want to make sure that we are training on each of the files and not on the special tokens themselves. So we kind of divide the file to find the chunk boundaries and all the separate tokens. And in this training loop, we are basically doing another step before the merge operation. And that step is right here. So firstly, we are declaring the vocabulary to be between 0 to 255 for all the individual characters. And we also are giving vocabulary indices to the special tokens as well. So we basically find the boundaries of this data file, and we basically do multiprocessing, basically doing parallel computation of processing each of the chunks and pre-tokenizing them. So pre-tokenizing is a way of making it more efficient. So rather than basically converting the documents into individual bytes, which would be very inefficient, we basically do some level of pre-tokenization. So this is what is usually done in GPT-2 tokenizer. We basically convert it into a lot of subwords which we already know would be relevant. And we basically create a local corpus for each of the chunk boundaries. And then we process, we basically merge all these local corpuses into a global corpus. And do the merge sequences on this global corpus. So you can definitely go through this code yourself. So the main aspect of the code which might be complex would be the multiprocessing of these various corpuses and why we are doing it. But this makes it much faster to process each of the chunks and pre-tokenize them and then work on them by merging the various pairs right here. So the pair counting, obviously we declared a default dict and we are counting the number of pairs for the various ones, finding the most frequent one, the merge token, uh, adding that to the vocabulary, adding them to the merges, updating the index, and also updating the new corpus, like updating the sequence itself to use the merged pair, and then it returns the vocabulary and the merges. So later on, when we initialize our tokenizer, which is a tokenizer class right here, we are basically going to give it the vocabulary and the merges. And when this tokenizer encodes the various files, it's going to refer to these vocabulary and merges and work on the text which it is given, and basically apply the merges to the text as well, and basically tokenize it and give the encoded IDs. So yeah, that is how this tokenization works in production, and you can definitely look at this GitHub repo and have a look at how this is being implemented here. Okay, so this is some brief overview of the transformer architecture so far. So on the left, you can see the attention is all you need paper and the transformer architecture which it proposed. It got some multi-head attention, some layer norms after these blocks, a residual stream and the softmax at the end. And on the right, you can see the architecture which I've implemented in my GitHub repo. So this is the one which you would also should be implementing from scratch on your own as well, because this is much more similar to how most open source LLMs at least, and definitely some closed source ones as well, are implemented. So the norm is over here before each of these blocks. And the rotary position embeddings, obviously that's one difference from the attention is all you need paper, that this has been quite recent explosion of rotary position embeddings in most of these LLM architectures. The linear layers use Swigglue. So most of my discussion is going to be why we used these different versions of this transformer and what changes we made and why we made them. To understand that, we can definitely look into various model architectures release. Even if you look at the last year, there's more than 20 new dense model releases with minor architecture tweaks. So Qwen 2.5, Command A, Gemma 2, Gemma 3, 5.4, the Nemotron from NVIDIA, and so many different ones. So going through the architectures for each one is definitely annoying. So there's definitely, but there's a lot of value to go into and look at the data of how each of the architecture differs, because almost all of them have only minor architecture tweaks. So we can definitely learn something from them. So this is a spreadsheet data which kind of shows the various architecture components of each of the models used, and this model releases in chronological order of their releases and how it evolved over time and converge on some key widely used techniques and tweaks. So we're going to talk about some of the major architecture and hyperparameter variants. What do all these models have in common, and what parts vary and what we can learn from them? And obviously a code walkthrough from scratch implementation of many of the components involved in them, because obviously implementing them would give you a much more nuanced idea of what actually goes into them, and the decision makings would definitely make way more sense. So let's start with this this diagram kind of gives you a good idea of the major transformer change. Like the layer norm has gone from post norm to pre norm, and this has been something which everybody agrees on almost from the start, is to use pre-norm as opposed to post-norm. So the original transformer paper did the thing on the left. So there were layer norms after every operation in the residual stream itself. So very early people realized that moving the layer norm outside the residual stream makes a huge difference. And this kind of makes intuitive sense as well, because the residual stream is kind of connecting the output to the input. And in case of a very deep networks, the gradient propagation actually happens to the residual stream. So if you have layer norms and other operations on the residual stream itself, it can affect that gradient propagation and probably reduce model training stability. So it's also visible from the data as well of pre versus post norm data. So if you ask why the pre-norm was originally developed, So the post norm stuff was quite unstable in training, which involved a lot of learning rate warm up style things to make it train in a stable way. So if you look at the earlier papers, you almost always see that this pre norm plus some other stability inducing tricks were used to basically remove the need for this warm up for the learning rate. And the systems work just as well. So prenorm was created to mitigate this, where the papers argued that the need for warm-up would go away if we use prenorm plus these stability-inducing tricks, as opposed to just using postnorm and then the need to do the warm-up for the learning rate. So this was initially what it was, but eventually obviously it converged into it being a much more stable architecture in general. So there are a lot of reasons why this might be the case. One of them proposed ones is gradient attenuation. So basically there are gradient spikes, much more gradient spikes in the post-norm case, and in the pre-norm case there's much less of them. So arguments like if you do pre-norm, the gradient sizes remain constant, but if you do post-norm, then it would blow up, kind of in the orange way. So obviously the much more reasonable argument is that the pre-norm is just a much more stable architecture in general. And Grok and Gemma 2 actually takes this approach of adding layer norms both in front and back of the architecture, kind of like here, both layer norm in front and the back of each of these individual blocks. And this has also proven to be slightly more effective in terms of training stability. And layer norm in the residual obviously is bad. I already discussed that because it's like an identity connection from the output layer to the start. So if you're training really deep networks, that'd be bad. So let's look at the formulas for the layer norm and RMS norm itself. So layer norm, obviously many of might be familiar with it, is taking the difference between x and the mean of x and dividing by the square root of the variance, which is basically standard deviation. And the epsilon is just added for stability purposes, and then you multiply by gamma and the bias term. So the gamma and the bias term obviously are the learning parameters. And the notable models which use it is GPT-3 and 2 and 1, GPT-J and Bloom. And many modern LLMs basically have started using RMS norm, and it has almost become an industry practice to use it. And it's slightly different. Basically divides x by the square root of the squared norm of x, and epsilon term as before for stability, and the gamma, and there's no bias term because bias terms have proven to be make the architecture much less stable during training. So this has almost become an industry standard with the modern leading cutting edge LLMs like Llama, the Palm, the Chinchilla, and the T5 using it. And if we look at why RMS norm has been widely adopted and is considered better, we can look at the fact that it's much faster and is just as good. So there are basically fewer operations. There's no mean calculation and there's no bias terms. So, but let me show you in code actually, be much clearer that way. Okay. So this is RMS norm, which I implemented from scratch. Obviously, you can directly use the PyTorch version, but I implemented it from scratch to give you an idea of what it's actually doing. So in the initialization constructor, obviously, I'm doing the RMS weights and putting them as the parameters. So this is the learnable parameters, and this is the model layer size. So in the forward pass, these are the exact same operations which I showed through the formula. Where we are squaring x, we are taking the mean, we are adding the epsilon term, we are taking a square root, and then we are dividing the initial x by the RMS. And we also took the Torch 32 version of this because it's much more accurate that way. So if you count the number of flops which go into this RMS, so x is the dimension, let's say btd, then the squared operation would take the b times t flops, and then mean calculation would take b times t times d minus 1 plus b times t. So this is the mean, and then adding the norm is b times t, and the RMS norm. So if you basically add up all these flops from these operations, you would see that we get 4 times b times t times t. So this is the total flops which are used in RMS norm. And if you look at layer norm, if you make some similar calculation for that, it comes almost double that. It's basically double the number of flops needed for RMS norm. Uh, but let's see if you look at, but this explanation itself is not good enough to justify the use of RMS norm. And this is because if you look at the number of flops used in large language models with this huge number of layers and parameters and lots of transformer blocks, actually the state normalization, which is this normalization stuff, and the softmax only take 0.17% of the flops. The vast majority of flops are actually in the feed forward network, and the attention and the matrix multiplies. So normalization actually reducing this 0.17% is actually not going to make a huge difference. So obviously flops does matter, but in this case it's actually not that much big of a difference to justify using RMS norm. But what is even more important than flops is actually memory movement. And we will definitely talk about memory movement in later lectures as well, of how important that is. But there's a lot of latency involved in getting stuff from the HBM, which is the high bandwidth memory of the GPU. And if you're able to do more operations on the cache of the GPU as opposed to having to take the data from HBM and transferring it and working on it, that would make it much more efficient at low latency. Uh, so if you look at the normalization stuff, it is 0.17% of the flops, but it takes 25% of the runtime because it involves a lot of data movement in the GPU, which is not ideal. So if we use RMS norm, then it uses much less data movement, and that is what actually makes it much faster and much more effective than layer norm. And layer norm, obviously, you can look at the ablation reports from, I couldn't find any recent ones, but this Narang ETAL 2020 provided a table which gave a very nice comparison for the various transformer architectures and using RMS norm versus layer norm, and you can clearly see that it's much better in terms of performance compared to layer norm. And obviously more generally accepted is dropping the bias term as well. Bias terms often cause instability in training. Obviously there are a few proposed explanations, but it's almost always widely accepted that a bias term is not really needed. It doesn't really improve the model quality and only makes the training much less stable. So now we also have the activations themselves. The activation functions, obviously there's a whole zoo of activations. There's relu, there's gelu, there's swish, there's elu, glu, reglu, silu, swiglu, liglu. So there are a lot of these different activation functions, and this is the kind of thing which I was not really interested in when I was learning deep learning, but actually they do make a huge difference. So relu is a simple activation function which outputs 0 for any negative input and returns input times the weights itself for the positive one. So this is obviously quite popular, and many of you might be familiar with this one. So this basically lets the positive signals pass through unchanged but completely blocks the negative signals. So this kind of helps the networks learn more linear patterns while staying non-linear patterns while staying computationally efficient. And Gelu is a more stable version, you can say, of Relu, where there's a slight bump near 0. So it stays differentiable throughout, which may or may not help. But yeah, that's the major difference between them. So it kind of increases the number of computations needed to implement Gelu, but the computations themselves are negligibly more, and obviously the GPUs themselves are really adapted to be able to do these kinds of computations. So that kind of concern does not really happen here, and it's the benefits of basically having more stable training with Gelu outweighs any of the extra negligible computations you might need to do. And the GPT families, models of 1, 2, 3 for the GPT family and Bloom all use Gelu. And some of the older models like T5, the Gopher, Chinchilla, and OPT use Relu. But almost all modern LLMs have switched to gated linear units, which is like Swiglu and Geglu. And the Google folks really pushed for this, the Palm, the T5, and the others. They really pushed for the gated linear units. Once it since it tried and tested right now, so almost all models in the last year 2023 have used gated linear units. So gated linear units basically modify the first part of the feed forward layer. So instead of using, so you can say that ReLU is ReLU's activation function, which kind of gates parts of the input using kind of a ReLU mask. And instead of passing a single vector through ReLU, it splits it into two halves. And one of them is the main signal, and the other half after ReLU acts as a gate that scales the main signal. So this kind of makes the network more flexible with like an element wise on off switch for each of the feature. So basically dividing the input into two different ones. One is kind of the gating mechanism and the other is the main signal, and basically doing an element wise product of them. So yeah, it kind of increases the amount of signal and amount of non-linearity we are providing. Uh, and this is for reglu. If we replace the relu with a gelu, then it becomes a gaglu in this. So yeah, it's an equivalent implementation for the reglu. Now, swiglu is a really popular one as well. It's used in many leading models. So the non-linearity here is x multiplied by sigmoid of x, which is called swish. Also, the gated models like this also have like hidden size to yeah. So gated models use smaller dimensions for the DFF by 2/3 because the total parameters we want to make sure the total parameters remain the same for the gated units as well as the non-gated counterparts. So we because there are two of them here, we try to make them the same. So we try to reduce the dimensions of W here to be 2/3. So I would just show you the implementations of swiglu to give you a better idea. So it should be right here. Okay, yeah, so this is the swiglu. You can see in the initialization function we have initialized DFF. If we haven't passed DFF, then we basically do 8/3 of D model. You might be wondering where this is coming from. So this is basically standard practice is for the linear layer to be 4 times the dimensions of the D model, and now we are taking 2/3 of 4 times of D model, which makes it 8/3. So we want DFF to be 8/3, and we also want it to be divisible by 64, obviously, because that is what the GPU expects and is much better and faster at performing such calculations when the numbers are divisible by 2 or 8 or 64 and stuff like that. And this is what we have discussed, the same formula where we have the gate and we have the value. We are taking the sigmoid times it, and we are multiplying them, the gate and the value together, and then multiplying by the outer weight matrix as well. So yeah. So yeah, so the gated linear units do work, as you can see in this table. This is kind of showing you that the final loss is actually lower for the gated linear units ones compared to non-gated unit counterparts. So yeah, there's quite a consensus among the research community that gated linear units do work, lead to better stable training, and also lower final loss as well. Uh, the normal transformer blocks are serial and they compute attention and then the MLP. So now I'm going back into the parallel versus serial layers. The title of this slide is actually wrong. It should be parallel layers. But yeah, so if you look at the attention block right now, we go to the norm, the casual multi-head self-attention, the dropout, the add, then the norm, the position wise, feed forward, the dropout and add. So all of this happens serially. So is it possible to parallelize this transformer block? Because there are definitely constraints here in terms of this not being parallel and everything independent on the previous layer. So a few models like GPT-J and the Palm and few folks at Google have worked a lot on parallel layers, where as you can see the MLP and the attention are initially used serially and depend on each other being completed before they can go ahead. But in parallel formulation, you can compute the MLP and the attention together and basically add them together to the residual connection. So if implemented right, then you can get some system level efficiencies. Like you can combine many stuff like layer norms and matrix multiplies in the CUDA kernels, and basically make your inference much faster. But most of the models in the last year have seen mostly serial layers and not parallel ones. Okay, so in the first few years of LM land, there was a lot of different things people were trying, various kind of position embeddings. So basic idea was to how we can encode the positions within the token embeddings themselves. So there was sign embeddings, there was absolute embeddings, relative embeddings, and eventually most of the industry and the research community's consensus was using RoPE embeddings. So most of the models post 2024 exclusively use RoPE embeddings. So just to give you a brief idea of all these different ones, firstly, the sign embedding is basically using the sinusoidal position of each of the tokens and creating an embedding out of that, and basically adding it to the token position, the token embedding. An absolute embedding is a similar one where we are not using the sinusoidal function to create the embedding. And the relative embedding is also similar where we are taking the difference between the two tokens and creating an embedding out of that. But the most important is, of course, the RoPE embedding. And the basic high-level overview of the RoPE embedding and the high-level thought process is that the relative position of the tokens is actually what matters when we are creating a token embedding, a position embedding. So if we are taking two tokens, the only thing which should matter is the difference between the relative positions rather than the absolute positions. Because if you're training a model on absolute positions, and in production or during inference, the users might give different context length and sequence lengths. So if the model is not trained or doesn't have enough training data for those sequence lengths, then its performance would degrade considerably. So the only thing which should matter for position embeddings should be the difference between them. So we can formalize this notion by considering this equation right here. We'll be basically creating we are considering a function f which works on x, a token x, which is at position I, as well as token y on position j. So the dot product between them should be completely defined by another function j, which takes both these tokens, and the only thing it takes other than that is a relative position between them. So it doesn't depend on I and j itself, but only depends on the difference between them. So this is a good way to understand what exactly we are looking for when we are trying to create these position embeddings. So the attention function only gets to depend on relative positions. And now if we take this formalized notion and try to evaluate the sign, the absolute and the relative embeddings, we can see that the sign actually leaks the absolute position. And the absolute embedding obviously is not relative. And the relative embeddings does go a long way, but it's not exactly the inner product. Because what we are looking for during the attention mechanism is that we are taking the inner products of the different tokens, and we want to make sure that the absolute position is not leaked through that. So it's not exactly an inner product. So that's where the RoPE embedding comes in. So just to give you a brief intuition of what exactly RoPE is doing, we can consider this series of, we can consider 2D dimensions for each of the vectors. So embedding dimensions usually obviously are like much higher. They're like 700, 800 dimensions obviously, but it's harder to visualize. But here we can consider a sentence, for instance, we know, and we can see that the angle between them. But if we add another word, we know that, then we can say that we rotate we by 0 positions and no by 1 position. And the angle between them remains the same in all these 3 sentences. If we consider the last sentence, of course we know, we rotate we by 2 positions and rotate no by 3 positions, but the angle between them remains the same. And that's the basic understanding of how rotary position embedding actually works. It want to make sure that the only thing that matters is the relative position between them rather than the absolute position. So obviously it was easier to see that in this 2 dimensions, but if we are implementing it in embedding dimensions, which can be 700 or 800 dimensions, it's much harder to understand what exactly is going on. But just to give you an idea, you can think of it like taking a long embedding dimension and basically chunking it in pairs of 2 and rotating each of those pairs by certain theta. And those theta can be different throughout the embedding vector. So the embedding dimension, usually the case is that the indexes which are much further off are rotated by a higher theta than the ones which are at the start. So that's how, yeah, this is a good way of showing this as well. Like basically matrix multiply with the embedding vector, where you can consider this to be a series of square matrices which basically multiply those pairs of tokens and rotate them by a certain amount. And yeah, just to give you a code idea of how it's implemented in practice, uh, you can consider yeah, this RoPE embedding implementation right here. So we are basically in the initialization function, we're taking the theta, the dk, which is the embedding dimensions, and the max sequence length. We are creating this inverse frequency, which is of dimension dk. So this would be the one which should be applied to each of the elements of the dimension. And then we are declaring this positions vector, a torch tensor where it's of length max sequence length, and then we are getting the angles by multiplying this position by this inverse frequency. So the positions which are much further off would have higher frequencies as well. And then we are computing the sine and the cos, and we are saving them to the register buffers so it's easier to access them. And in the forward pass is where we are actually applying it to a particular tensor x, and we also have its token positions. So we get the sine and the cosine for all the token positions, and we split it into the pairs which we want. The even and odd indices, that's usually how it's done in practice. The even and odd indices for the whole embedding dimension, and basically rotating each of those pairs using this rotate even and stacking them together, flattening them. So that's usually how it works. And another advantage of RoPE embedding is actually we can increase the context length during production. If you want to change it, we can change the theta, and we can make this much more compressed or much more wide depending on whatever we want. And there's also another extension of RoPE embedding called yarn, which I would discuss in future lecture, where we are basically making it much more generalizable to different context lengths during production. So yeah, that's a really interesting extension of this as well, which we can talk about in the later lectures. Okay, so now we can go one more level into the details here and talk about the hyperparameters. So I think when you're asked to train a language model, there are a lot of questions about hyperparameters because there's so many of them. But actually only a few of them really get changed over successful models. So there are fairly rigid guidelines and rules that people seem to be following. And if you're able to follow them, then you will get a decently sized and well generalizable model. So hyperparameters obviously like how much bigger should the feed-forward size be compared to the hidden size, how many heads and how much number of heads should be there, and what the dimension should be for them, what should the vocabulary size be, do we need to regularize these large language models, and how do people scale these models, whether it's very deep or very wide. So all these questions are quite important, but there is surprising consensus among many of them for the research community, and they have studied it well, and most of the research labs are actually very conservative in terms of hyperparameters, and they rely on one another and don't take too much risks on it. Google is one exception. They have trained some quite few models with pretty bold settings, and I would be discussing them as well. So the first surprising, I guess, consensus on hyperparameter is, let's say the starting point is a simple feed-forward network, the ReLU version of it. So there are two things, the D model, which is the dimension of X, which is the input, and DFF, which is the dimension of those weight matrices in the feed-forward dimension. So it's kind of the hidden dimension of this MLP. So what should this DFF be? So usually these are supposed to be up projections. So there should be more hidden units than there are inputs. But how much bigger should it be? Well, there's just like a consensus on this as well. Like most who use the ReLU style feed forward use a DFF which is 4 times the D model. So yeah, most of them use it. There are definitely a few exceptions. And obviously one of the exceptions is GLU variance, which is the gated linear units, which I previously discussed. So the gated linear units obviously involve 2 weight matrices. So it's actually just to keep the number of parameters of these gated linear units to be the same as their non-gated counterparts. It actually scales down the number of parameters for each weight matrix by 2/3. So actually the DFF is 4 times 2/3, which is 8/3 for this GLU variance for the models. And if you look at these various models, you can probably see that all of them do satisfy this 8 by 3, or which is roughly 2.66. Palm is 4, which is quite off. It's a GLU variant as well, so it's supposed to be 2.66, but it's 4. But it still works, so it just goes on to show that there is nothing rigid about these settings, but it's general guidelines, I would say. And most of the other models like Llama, Qwen, and DeepSeek, and T5, they basically, yeah, they fulfill this ratio pretty nicely. Yeah, one of the exception T5 as well. So it's one of the different things about it is that one of its variants, the 11B model, actually uses very bold settings. So as I previously said, most of the models are pretty conservative in terms of hyperparameters, and they don't really experiment very much because training is pretty expensive, and you want to make sure that you do it in the most cost-effective way, in a tried and true and tested way. But they use a 64 multiplier, and they still have a decent model. So yeah, this is one of the exceptions, I would say. And the Google folks obviously tend to take quite a few risks every now and then to see what works and what doesn't. This is one of the charts from the Kaplan 2020 paper, the scaling law paper. So other than the scaling law, that paper actually had pretty interesting insights into the hyperparameters as well. And this kind of gave you a data of DFF by D model for each of the different parameters for the model, and you can see that there is a minima. So there's a pretty wide range where the loss is minimized for DFF by D model. So if you choose DFF by D model of anything between, I guess, 1 and 10, I think it would be decently okay for most models. Another consensus hyperparameter for the research community, of course, is the number of heads. So in multi-head self-attention, we are basically dividing a singular head into multiple heads. So if we are dividing, say, a head into like 5 heads, then each one should have 1/5 the dimensions, and that would really make it the same number of parameters either way. So that is a pretty good guideline, general guideline, which many models follow, of the number of heads, and the dimension is just divided by the number of heads. And most models do follow this. Yeah, you can see here some examples of this hyperparameter where models are following this. Of course, T5 has this ratio of 16, but most of the others are 1, 1, 2, 1.48, 1. So most of them are, yeah, very close to 1. Yeah, this is one of the things which is, and one more thing, the T5 did have 16 for this, but it actually performed quite well as well. So it just goes on to show, yeah, nothing is rigid. And this paper as well is from Bhojanapalli et al. 2020, and this kind of makes a case against the 1:1 ratio. But again, there are obviously research community consensus on 1:1 ratio, and it has proven to work. But it just goes on to show that there's some evidence of the contrary as well, and experimenting more in this direction can provide fruitful results for what kind of hyperparameter settings might work with different models. Aspect ratio is how deep and how wide the model should be. So most models are also surprisingly consistent on this one as well. So if you look at the GPT-2, there's a sweet spot of between, I guess, 100 and 200 or something. But most of the models, if you look at GPT-2 and T5, they have they're relatively small ratio for D model by N layer, which means the models are very deep, and the Bloom and the T5 are very wide. But there's a sweet spot of like Palm, GPT-3, and Llama, which work pretty well as well. So yeah, aspect ratios don't really, I would say, are not extremely effective, or like they don't make that much influence on the final model performance. But one thing that do actually affect is the deployment of models. So if you see very, very deep models, having different layers on different GPUs is actually less effective and cost efficient. So it actually, the networking capacity of the different GPUs can be a bottleneck when you're deploying very deep models. As opposed, if you have very wide models, dividing the parameters between the different GPU during inference can actually be more cost effective. So that's the only thing which aspect ratio might affect, is the actual deployment of these models on the GPUs. Yeah, this is an example, another graph from the Kaplan paper talking about the aspect ratio. And again, there is a pretty wide minima, I would say, of the aspect ratios we can use, between 10 and 100, I guess, or maybe 200 as well. So yeah, the graphs on the right kind of show that there's not much effect of the aspect ratio on the final model performance in terms of perplexity, but actually very deep models performed slightly better on general benchmarks of superglue accuracy. So there might be something about the deep models which work well in the superglue evaluation. So yeah, definitely evaluating your models on these different benchmarks and seeing what works and what doesn't for your use case might be slightly helpful. Okay, so another interesting thing in hyperparameter is vocabulary size. So we could have discussed it sooner in the lecture as well when we were discussing tokenizer, but now it seems like an appropriate time as well. So for the vocabulary size, there are the major thing which we would need to consider is the linguicity of the model, like how many languages and stuff it's going to work on. So obviously in the recent times, the vocabulary size for the models is trending upwards. And this is primarily because LLMs are being deployed in the wild and people are using different languages, different emoji expressions. So yeah, that's why the vocabulary size is increasing for the models. And if you look at the monolingual models, it's common to have vocabulary of 30 to 50,000. And multilingual systems, it's very common to have 100 to 250,000, because obviously if you're working on multiple languages, there are all different kind of things which comes into play there. And Command A, which is a Cohere model, was recently announced. It was 255,000 vocabulary size, which is pretty big. And Command A, Cohere obviously have a huge emphasis on multilingual systems, so that definitely makes sense. And there's also evidence that as models get bigger, they make better use of the vocabulary size and their performance actually increases. So this makes a lot of sense that as models are getting bigger, the vocabulary size is also increasing. Okay, another interesting discussion is about dropout and regularization. So a major question is, do we even need regularization during pre-training? Because obviously pre-training is something which seems the furthest thing which is furthest away from regularization, because we are doing a single epoch over the whole training corpus, which is huge. So we don't even have time to do a second epoch. So overfitting doesn't even come into play. So what exactly people do in practice in terms of regularization or dropout? Are they doing it or not? So this table kind of gives you an indication of previous models and what kind of dropout and weight decay they used. And most of the recent models actually don't discuss dropout at all, and that usually means they didn't use it. But weight decay is something which has consistently been used and has actually increased its popularity with the current epoch of LLMs, current era of LLM training across many different domains. So let's see exactly why weight decay is actually quite important in pre-training. So if you look at these graphs right here, it kind of gives you an indication of exactly why weight decay is being used currently. And it's not exactly to regularize the model. For instance, on the rightmost graph, you can see a constant learning rate and how initially, when the learning rate for the model is quite high, the training is not going as well. But as the learning rate reduces, then the graphs where the lines where we have the weight decay actually rapidly reduces. And similarly for the cosine learning rate decay in the middle graph, we can also see that training dynamics are much better for the weight decay ones. So weight decay actually has a complex interaction with the learning rate scheduling and the optimizer. And the reason we use weight decay during pre-training is for this complex interaction which we do not fully understand, but it actually makes the training dynamics much more smoother. And that's the main reason we use weight decay. It's not to regularize it, but to actually make the training dynamics better, and it ends up reducing the training loss and the validation loss to some extent. Okay, so now let's discuss more about stability tricks. So obviously recently with all these companies and these labs working on training these models, the stability of the training has become extremely important. And we want to make sure we do the best stable training as possible. And yeah, these graphs shows you what exactly unstable training looks like. So you can probably see the orange and the blue curves. So the orange curve is kind of stable, and the blue curve in the initial graph on the top, you can probably see the loss spiking every now and then, but it doesn't look too concerning. But if you actually look at the L2 norms of the gradients, it looks absolutely ridiculous and is a nightmare for any ML researcher to see such kind of graphs. So this is the kind of thing which we are trying to prevent, this unstable training. And the orange curve on top, actually, it seems its loss is higher, but it's just might be different data, training data or something. That's not really the point of this, but the point of this is to see that the stable versus unstable training and the huge amount of difference in terms of the L2 norm of the gradients and other spikes you can see. So the goal of this is to prevent what is happening in the blue curve. So here, so where do these issues arrive? So most commonly it arrives in softmaxes. Obviously it can arrive in many different places in neural networks, but one of the major ones actually is softmaxes, because they involve a lot of exponentials and division by zero. So where exactly do we find softmaxes in our architecture? So you can see it probably near the output layer, and it's also actually part of the casual multi-head attention. So we have many transformer blocks, and each one has multi-head attention, and each one would have softmaxes within them. So there are quite a few softmaxes in any neural network architecture with this transformer kind of thing. So we have a few tricks we can use to prevent the softmax from blowing up too much. And one of them is the Z-loss trick. So there was this machine translation paper by Devlin in 2014, and the goal was to make sure that the normalizer Zx was near 1. So recall that the softmax calculation involves the logarithm of the exponential of the logits divided by the Zx. So the whole goal of the paper was to try to make Zx equal to 1, because that actually makes the softmax much more stable. And the solution they proposed was actually adding an auxiliary loss term to the loss function. And the loss term happens to be the logarithm of Zx, and we are trying to make this 0 in the loss, it's in the custom loss. And once we are able to do that, then it becomes 1 in the softmax, and it stabilizes softmax quite dramatically. So yeah, eventually it was adapted by Palm, and it was used and it provided a lot of stability for the softmax function during their training, and it has since been adopted by a few other models like Bytune, DCLM, and Almo as well. So yeah, this is the Z-loss trick. Another thing we can do is logit soft capping. This is not quite as frequently used because it might cause performance issues in some way, but is still proven effective in some other cases. So the idea is to take the inner product after self-attention, and instead of directly using the logits, we pass it through this equation where we divide by the soft cap, apply tan h, and multiply by the soft cap. So what would happen if the logit is too big is that the tan h would be 1, and it would cap it to the soft cap. So it's kind of capping it and kind of soft clipping the logits. So yeah, this tames the behavior of the softmax somehow, but it might cause performance issues because it reduces the variance of their outputs. And there was this NVIDIA study where it kind of showed that it might not be as effective compared to other strategies. But still, logit soft capping does work in taming the softmax issues of gradient spiking and such other things. So the last thing I want to talk about is attention heads. So attention heads don't have as much work on them as other aspects of the transformer. But the first thing I would like to talk about is GQA and MQA, grouped query attention and multi-query attention. So these are not as essential to talk about in terms of the training behavior of the model, but they actually make a huge difference on the inference time and the inference cost of the model. And the other thing I want to talk about is kind of a new development. Like if you look at models like Llama 4 and some other new Gemma models, they have 10 million token of context. So how do these models do that? So basically do that by messing up with the attention pattern in a very structured way. So I'll be talking about that as well. So just to motivate the need for GQA and MQA, so if you look at the self-attention pattern right now, implemented, it's and count the number of arithmetic operations which go into them, you can probably convince yourself by looking at this that the number of arithmetic operations would be b and d squared. Like if you count the number of matrix multiplies of the queries and the keys, as well as the softmax operations and the final projections. And if you look at the total memory accesses, like the number of things, parameters, and activations which you would need to download from the memory to the registers to process, then that would be b and d plus bhn squared plus d squared. So b, of course, is batch size here, n is the sequence length, and d is the hidden model dimension size. So the arithmetic intensity of this training is actually pretty good. So arithmetic intensity is kind of a metric of finding out how many arithmetic operations you are doing for a given memory access. So if you're able to do a lot of arithmetic operations for a given number of memory accesses, then that's good, because higher number is better, because GPUs are actually really good at computation, and the only bottleneck is loading and uploading and downloading stuff from the memory, which takes a lot of time. So I want to do as much operations as we can after we have loaded something from the memory. So that's the basic idea of it. So in training, as you can see, the arithmetic intensity is pretty good, and there's no need to optimize this. But the question comes when we go into the inference time. So this is a really nice simulation here, which kind of gives you an idea of what is happening during the inference, because we are auto-regressively decoding this model. So we are using the query from the last token and the keys and values from all the previous token to basically predict the next token. So we need the keys and values of all the previous tokens, and we need to load them up in the memory registers of the GPU every single time from the high bandwidth memory. And doing this a lot of time actually is one of the major bottlenecks of it. So memory access pattern changes during inference compared to in training. So yeah, keys and values, I guess we also have I can talk about the concept of the KV cache. We are saving these keys and values of all the previous tokens instead of recomputing them every time, so unlike the way we were doing in training. So we'd be saving the keys and the values in the memory and loading them every time we need to make a prediction for the next token. And this is the major thing which basically changes in inference time, this memory access pattern. And increasing memory access pattern obviously reduces the arithmetic intensity and hence inference cost, as well as the inference latency of the model. So as you can see here, we need the arithmetic intensity to be as high as possible. So we need large batch sizes either, or we need short sequence lengths, or we need big model dimensions. So the way we are thinking of solving this is, of course, the n by d term is difficult to reduce. So this is where we can motivate the use of GQA and MQA. So the basic idea of multi-query attention is that there are multiple heads. So the keys and values and queries for all these different heads. The basic idea is the queries can be different for different heads, but the keys and the values can be the same for all the heads. So we don't have to load keys and values for all the separate heads separately, because that increases the memory accesses by quite some amount. So if we are able to keep the keys and values common for all the heads in the attention mechanism, then that would change the total memory access and would increase the arithmetic intensity, which our overall goal is. And the grouped query attention is also kind of an extension of this, you can say, because instead of having a separate keys and a same key and value for all the heads, we group the heads into groups, and each group would have its own key and value. So it kind of is a middle ground between going all the way into multi-query versus multi-head. So grouped query attention is one. So does the MQA hurt? So the data just does so that multi-query attention does hurt slightly some of the times, but obviously there's not a lot of evidence on this. But the grouped query attention definitely has negligible impact on the model performance. Now let's talk about the sparse and the sliding window attention. So this is a very interesting development in the last few months as well. So in 2019, OpenAI had this really cool paper, basically arguing how to build a longer attention model. And one way to do it was basically building these sparse attention patterns. So instead of paying attention to all the sequences, we are going to pay attention to only say a local window at each sort of chunk. And can have other attention patterns, say kind of like these diagonal ones, which propagate attention this way. So we can build like these sparser structures of attention instead of full attention and make it better and less computationally expensive. So we can reduce the expressiveness of the model at the cost of the runtime. And this is an example of sparse window attention. So sliding window attention is basically where a token gives attention to its nearby tokens within a certain threshold. So obviously this also reduces the computational need and improves latency and other stuff. and improve allows the models to have much longer context lengths, because the computation doesn't scale quadratically if you use sparser attention patterns, including the sliding window one. Okay, so these were relatively old ideas, but what the modern instantiation of these ideas, you can probably look at papers from Llama 4 and Gemma and Cohere Command A, which talks about this very clever trick about having these transformer blocks where we have like these four transformer blocks, where the last one is full self attention and has no position embedding. So it gives full attention to the whole sequence and doesn't care about the positions of the tokens and works for the full sequence. And this happens every four blocks. And the rest use sliding window attention. So this is kind of a neat way of controlling the systems aspect of things by because we only have full attention, which happens only every few blocks, and also have the length extrapolation because rope embedding only deals with kind of a local context windows, and anything which is really long range has no position embedding at all, so it can extrapolate very nicely. So yeah, this is basically what the modern instantiation of the kind of sparse attention patterns we were talking about, how they're actually implemented in most of these modern LLMs. So hopefully, yeah, this was helpful for some of you, and yeah, thank you so much.